Hey, I'm Federico. I'm an engineer at TigerBeetle, and as the song alluded to, we're going to be stepping into the danger zone today. We're going to reach beyond some sort of standard language tooling, and we're going to explain about how we handle upgrades in TigerBeetle. I'm assuming a lot of people here might not know what exactly TigerBeetle is and why this problem arises. So before jumping in, I'm actually going to just give a little overview of TigerBeetle, of Zig, of things we use. Then we're going to go through how we solved this upgrade problem across the 3 platforms we support, Linux, Windows, and Mac, as well as the friends or bugs that we encountered along the way. Maybe there are going to be some useful takeaways for non-systems programming people, but, well, no promises. So before we get into that, for those of you not familiar with it, TigerBeetle is a high-performance financial transaction database, and it is written in Zig. It's fully open source under Apache 2 license. It's ready for production workloads, and it is currently serving high-volume traffic for customers in production. So I actually have no idea where these Google suggestions came from. But I promise you, you won't actually need to know anything about accounting or Zig for this talk. So, a little bit about Zig. Zig is a systems programming language created by Andrew Kelly. So the sort of going analogy for it is you can think of it as what Rust is to C++, Zig is to C. Please do not dig too deep into that analogy. But one of the important things to know about it for this talk is it allows us to really easily build TigerBeetle as a single statically linked binary. Now, of course, this is possible with other languages. Zig gives it to you as the default, and it also gives you amazing cross-compilation out of the box. I say statically linked library, this statically linked executable. This is only possible on Linux. On Windows and Mac, you still do need to link with some system libraries for various reasons. But enough about Zig. Let's talk a little bit about TigerBeetle. TigerBeetle has a fixed double-entry accounting data model, and it doesn't use SQL. It can do this reasonably because it's got a very tight problem domain, namely financial transactions. So in TigerBeetle, there are accounts and there are transfers. Transfer debits one account and credits the other. You might recognize this. This is very simple double-entry accounting. This was used by the Venetians hundreds of years ago, and you might have done it in high school or even junior school in some places. If you're not familiar with it, you can think of it as a ledger. Every transaction is strictly two-sided, a debit on one side and a credit on the other. By baking this actually into the data model itself, you can get a really powerful guarantee that no money is created or destroyed, by accident at least. If you move 100 euros from Alice to Bob, for example, double entry accounting ensures that there's always an equal and opposite entry. You can't end up with 100 euros appearing out of thin air. TigerBeetle takes this simple data model, it couples it with high performance, so in the order of hundreds of thousands of transactions a second, consensus, deterministic simulation testing, network, storage, fault models, and for good measure, there's some static memory allocation thrown in. And under the hood, TigerBeetle is this fault-tolerant distributed system. Well, maybe if you don't run it all inside US East 1, at least. Normally, it consists of 6 replicas that all keep the same state. These replicas sync using view-stamped replication, and there is a quorum of replicas that have to agree on every transaction, giving us strict serializability. This consensus, of course, also means that we can fail over if the primary crashes, and another replica will step up without losing transactions. We take this log over there, we couple that then with the accounting state machine that I mentioned earlier, and you now have a state machine that's replicated across a bunch of machines, giving you a replicated state machine. This state machine the state machine needs to be deterministic across all the replicas. So given the same set of operations from the log produce the exact same byte-for-byte output. This is required because TigerBeetle relies a lot on what we like to call the physical determinism across replicas. So in the data file itself, it's split up into 512 kilobyte chunks, and for a certain chunk at a certain part in the data file, this is going to be identical, byte for byte, hashing to the same value across all replicas. This gives some very nice properties. It means that state synchronization is incredibly fast. So if you have to repair a data file on a particular machine, or you need to do any sort of operations like that, you can compare them physically. You don't need to do anything more advanced. And it also means that you can essentially hash the data files minus a bit of specific information and get to the same hash across machines. Excuse me. So this might seem straightforward at first glance. So this is an excerpt of some code from our state machine, and it's barring all of the Zig-specific syntax and some weirdness. It's actually relatively straightforward synchronous code. It, here checks if something is equal to 0, returns must be not 0, returns must be not maxed int. And it's about 7,500 lines of this, but each function in and of itself is very easy to reason about. The problem comes with some of these lines at the top of the file. So while it might be easy to think of the state machine as just the accounting logic, the state machine also incorporates a full LSM tree implementation that we built in-house. And this is slightly more complex because it makes heavy use of asynchronous concurrent code. How can you be, so you can see we have dispatch loops and all the like. How can you be deterministic and concurrent? So we use barriers heavily. Work is actually split up and scheduled based on incoming traffic. So that is when a client sends a request into TigerBeetle, that request is what actually drives our LSM compaction work forward. It doesn't run ahead at its own pace like in a lot of other systems. So ensuring that all of this is deterministic is actually quite manageable when you're dealing with a single release, right? You're running the same binary, and unless you're doing something explicitly non-deterministic, or you have a bug in your barriers, there's a possibility, things will work. So for those cases, we have explicit tests, simulations, assertions. TigerBeetle has thousands of assertions that run turned on in production, and those will crash us if non-determinism is ever detected. However, when upgrading things, when running different versions in a single cluster, this becomes unworkable. The number of combinations explodes, and it's too easy to inadvertently make a change in some logic like this that might affect what data is stored in which block on disk. We've had people who run similar architectures sort of internally tell us what a common way of doing it is. They would replay weeks of existing production traffic, and then they would verify that the state at the end matches the state they expect. And even in those cases, there's still changes that drift out of sync, and then they have to introduce other changes to kind of drift it back. Ideally, that's definitely not the right slide. Whoops. Ideally, what we want is the guarantee that a given operation from the log is executed by the exact same state machine across all replicas. And one easy way to do this, that sounds quite simple, is you can actually just SSH in to a cluster, stop TigerBeetle on each machine, then put in the new binary, and restart TigerBeetle. So you never run it across different versions. This is simple, but now you've traded your deterministic simulation testing, everything that you have before, for the consensus of myself, the operator, sitting behind a keyboard, manually SSHing into machines. Maybe I haven't had my coffee for the day and I make a mistake, who knows? You're relying on me to check things like, is the cluster healthy before I shut it down? Best case, you're also causing, multi-minute long downtime. What happens if the power goes out midway through? That's actually, that's actually not a dig at current events. I'm from South Africa, and some of you might know power outages there are a thing. My South African immune system is not up to the viruses and such that are found in Europe. So, what happens if my Windows laptop decides to install updates, or my Linux laptop's GPU decides to stop responding? And no, the answer is not to use a MacBook. What if we could take and use the very consensus that we've built and tested so thoroughly to also handle the upgrade? Like, after all, right, we're a database. Like, storing things durably is kind of what we do. So that's the solution we settled on. Push the upgrade through consensus and through the log. That's great, and it handles the logical part of the upgrade. But now a cluster knows what version it should be running, but it doesn't help with actually running it. And that's where, as the title of this talk spoiled, multi-version binaries come into play. Having a single binary is something we consider critical for user experience on all platforms. One binary, one data file. No messing around with libraries. Sure, Docker is supported, but it's easier to get started with a single static binary, and in fact, it's our recommended deployment method in production as well. The fewer layers of abstraction you put between TigerBeetle and your raw disk, the better. TigerBeetle can also be deployed in a bunch of different configurations, right? It's not a proprietary system. You could be running it on Docker, Kubernetes, probably only those two, really. I'm sure there's still some others. I don't know if people still use Docker Swarm. And while we'd love for you to use our managed product to handle all of this, coming soon, having multiple files or things that can go out of sync just is not going to be a good experience. So what we do is we take multiple passed TigerBeetle binaries, the actual binary themselves, as well as some metadata that's used for physical releases, and we embed them into a single TigerBeetle binary. So you can actually, when you download a TigerBeetle binary off GitHub, it's essentially multiple little TigerBeetles wearing a trench coat, pretending to be one. These releases aren't specially compiled or specially modified. They're the actual past release binaries, just with their own past binaries stripped out and embedded into the single binary in a platform-specific manner. Linux is our only production target, but we do support Mac OS and Windows for development. And we really wanted to ensure a good developer experience. So even if deploying a cluster of, say, 6 MacBooks to run your central bank payment switch isn't a recommended deployment method, we still want TigerBeetle to work as reliably and as durably on these other platforms. So it was important that whatever solution we settled on could work across all three. Embedding files into binaries like this isn't particularly new. Some useful things like self-extracting archives and installers have been doing this, of course, for ages, as well as some other useful thing like viruses. We actually had a case where a TigerBeetle Windows executable got detected as a virus because it's kind of engaging in some behavior that might look suspicious if you consider it's extracting itself and then running another executable embedded in itself. But before I get into that, there were a few ways of actually building this binary that we looked at. So the one was we could compile TigerBeetle as shared libraries and then have like a wrapper that loads them into memory. That you load them as shared libraries into memory. We could also embed binaries directly using Zig. So Zig has this very cool @embed file compiler built in. So this will give you the content of a file at disk as just a sort of constant char string. So you could theoretically have your binary, load it in, and then write it out to a file. If you've used anything like GIMP's save as .h or .c file, this allows you to do the same thing really easily. We could also do it manually, modify or build our own binary using new additional sections. So this is the approach we chose in the end, namely because we wanted direct control over how things would be stored. Specifically, so that we could include backwards compatible metadata that would actually allow past versions to read the new version on disk, and this greatly speeds up the upgrade process. We also did not want the distinction between a wrapper and a launcher and the database itself. We just wanted to be one executable, and we wanted to have like a more peer relationship than parent-child. For Linux, this was relatively straightforward. Linux executables are ELF files, and adding extra data to an ELF file in a structured manner is really easy. There's a tool called object copy, and it's well supported. It's how things like debug symbols and sort of all sorts of other embedded data present in these files. We do almost the same thing. We embed 2 extra sections with well-known names that we can then look up at runtime, one for the pack of past binaries and one for the metadata associated with that pack. We can then parse them back out at runtime and write them to a memfd. So a memfd is a Linux-specific thing that is a memory-backed file descriptor, and it allows you to write to a file that you can then use with all of the other syscalls that expect a file descriptor, in this case exec. And it's nice is that it allows us to write out this release to something entirely in memory, verify the checksum, and run it without the potential for any races or stuff. And it was very much designed for this purpose. For Windows, which uses PE files, fortunately it doesn't come across too well, but this whole section of the PE file is labeled as like the optional header. I think it's only optional if you're running on DOS. Little historical quirk. The other quirk is that section names in Windows are limited to 8 bytes. But that's not a problem. We just shorten out our names, and we can do the same thing for Windows. In fact, parsing the Windows one is even easier, because with an ELF file, the headers, or I shouldn't say headers, the information is kind of scattered all around the file. So you have to do a lot of reading of tables and jump into locations. With Windows, you can sort of just say, I know the header's not going to be larger than 4 kilobytes, read in 4 kilobytes, and read it into structs and go from there. When it comes to actually running the binary now, the embedded binary, it's quite a bit more janky than on Linux. Windows doesn't have exec, it only has create process. So you can only start a new process, you can't replace an existing one. This kind of still works, actually. It works fine. There's a bug where in running it in the command line, TigerBeetle will still have control of your input and output, but you will also be at the command line prompt too. So even though you can type commands, if you hit Control-C, TigerBeetle will stop. It's a little bit weird. Mac OS uses Mac-O files. I'm kind of the opinion they should be called macho files, because they use like this really complicated sequence of like load commands rather than just a simple struct header that can be parsed and generated easily. In fact, some of the tools actually end up breaking when you try, and these are tools from LLVM, actually break when you try and just naively add a section like we did for Linux and Windows. So re-implementing all of this really wasn't something we felt like doing, but thankfully there was an escape hatch. So TigerBeetle ships universal binaries. So the binaries on macOS work on both x86 and ARM machines. Nothing says, however, that we can't include some extra platforms that have never seen a macOS release. And thankfully, the universal binary format is much saner with fixed structs that's really easy to construct and parse. So that's why if you download the TigerBeetle release for macOS and you run file or a similar command node, you'll see that it actually includes a binary for VAX, ROMP, and a few other esoteric old-school systems. Those are actually the embedded binaries hiding. Cool. I think it's time for a quick demo. This is going to be fun to, let's see, do that, do that, do that. Cool. So this is just formatting 3 data files. Don't pay too much attention to this. But let's run TigerBeetle. Whoops. Let's try that again. So over here, I'm just formatting a TigerBeetle data file. I'm formatting a TigerBeetle data file. And what I'm going to do now is I'm going to start TigerBeetle, a single replica on that data file. So it's running. It is running on version 0.16.39. Okay, let's open a new window. Zoom in a bit. Let's extract a new version of TigerBeetle. And let's replace it. Cool. So what's just happened here is TigerBeetle has noticed that its binary has been updated on disk. It has, if I scroll up here, yeah, detected that the binary has changed. It's gone from those releases to those releases. We can see we now have 0.16.40. Automatically kicks off the upgrade process, and then it actually re-executes itself. And it's now running on the latest release automatically. This is a single replica, so this is perhaps not that interesting. Let's actually run this multiple times. So 1, 2, 3. Okay, so we're now running 3 TigerBeetle replicas, 0, 1, and 2 over here. Let's actually mix it up a bit. So rather than running all of those from the same binary, I'm actually going to run a separate binary that I've copied here. Whoops. I need to extract the correct release after I upgraded it. So if we format. Okay, right. So these two are running from one binary, these are running from a different binary. The binaries are the same version, they're just copied into different paths on disk. So say now, for example, I overwrite the binaries that the two on the left are using with the latest version. You'll see that they've detected that the new binary is in place, but no upgrade's happening yet because the whole cluster doesn't yet have it. This is probably one of the most dangerous points in the upgrade process if it weren't for multi-version binaries, because what could happen here is a replica could crash and it wouldn't be able to come up because it's on a different version that's incompatible. The great thing about multi-version binaries here, let's Control-C one of these. We start it up again. It actually detects that it's not on the correct release, and since we have the binary embedded in it, it executes the past release internally and comes back up, no problem. Then once we say copy the updated binary over the one that's used over here, it picks it up, It now starts advertising that it's available. All of the replicas pick it up that everyone has the latest binary, and they all coordinate the upgrade and upgrade seamlessly. Cool. So, were there any bugs in this? I'd love to say no. That's all excerpt from the proxy tunnel man page. But the reality is there were a few, some of them more interesting than others. So the one that I found relatively surprising, but kind of makes complete sense, is that short reads are repeatable. If you're familiar with the read, like the read syscall when reading from a file in Linux, it tells you, retry until you get 0 to signal end of file, because you might read less data than you were expecting. If you give it a 8 kilobyte buffer, you might read 2 kilobytes, and that doesn't mean there's not more data. It just means that you're not getting all the data in one go. What was really surprising was that this happens consistently. What's happening behind the scenes is the kernel is giving you the data that's in the page cache, and if there's nothing else going on, it's going to give you that same 2 kilobytes every time you call read. Because I took a shortcut when writing this very code to try and not implement a loop. Anyway, other one found by, shall we say, a well-known database researcher. There was a race condition in that we do a lot of checks to ensure that the binary is the same on disk and what we're executing. And we do buffer it in memory. But we would then be in a situation where we could execute into the correct binary because we had it loaded in memory, but we were checking the file instead of checking the data we had loaded. The other one, bounds checks, interestingly enough. Zig has really good built-in, really good. It is good built-in safety and things like bounds checks and the likes. This kind of actually works against us, because when we're parsing a file, it's different from a lot of what other things TigerBeetles do, where you want to crash if something goes wrong, because it signifies a program error. Here, someone might drop in a corrupt binary. You don't want to crash then, you just want to print an error out. So actually reasoning about and explicitly checking all of these things that we were just kind of used to getting for free from the compiler. So sometimes it's good to drop down a level of abstraction, even when that level is into the operating system. I guess it helped that we weren't afraid to look and use these raw syscalls. A lot of this is using raw syscalls that aren't even supported by the Zig standard library. The other thing that we did was we used existing guarantees. We already had a well-tested consensus protocol, and we reused it instead of trying to invent something new. By making upgrade go through the same log, we could rely on all the testing infrastructure that we had built out. Problems lie at the edges, always. We built a fuzzer for this. There's no better feeling than looking at a piece of code that you think is bulletproof. How can there possibly be bugs in this? You write a fuzzer in 10 minutes and you found 10 crashes, right? Things like there would be size values. So if you had 255 multiplied by something else, that would now overflow. So these things can cascade, and it's always, always at the edges. And the last thing that we really wanted to do is just embrace simplicity for the user. We wanted the end user to have to do as little work as possible, because it's more work for us up front to build all of this, but multiplied by all of the people using the product, it's a big saving. Thank you. Any questions?